In this last segment of the agents lecture, we're going to see the mechanism a bit more in detail, and we're going to lift the veil on some of the possible mysteries that existed in the prior uses of agents. We had used them, but we hadn't seen all the details of how they actually work internally. And this also means that we need to take a look at the notion of tuple, which we have already used, without introducing it formally. So actually we start with tuples. You can write tuple, you can define the type tuple of A, tuple of AB, tuple of ABC, and so on. And what does this mean? Well, we've had the informal view before. Roughly speaking, tuple of ABC describes objects that are made of three components, one of type A, one of type B, one of type C, but it is not quite exact. The formal definition is that a tuple of type, for example, tuple of ABC, is a sequence of at least three values, of which the first is of type A, the second is of type B, and the third is of type C. So this is the exact definition. So for example, tuple covers absolutely all possible tuples, because it means a tuple of at least 0 values, and tuple of A means sequences of at least one value, of which the first is of type A, and so on. We're not restricted to having the exact number of components given in the tuple type definition. We can also have tuple values. So for example, A1, B1, C1, D1, where A1 is of type A, B1 is of type B, and so on, is a tuple of type tuple of A, B, C, D. This is how we denote tuple value. So you can see what tuples are. They are sequences of values of fixed types. Think of arrays. An array of type T is a sequence of value of type T. And of course the difference is that in an array, all the elements have the same type, or a compatible type, a type compatible that conforms to T, but the number of elements is arbitrary. In the case of tuples, the elements do not have to be all of the same types. In this example, tuple of ABCD, there is an element of type A, an element of type B, and so on, so the types can be different, but the number of elements is not arbitrary. In this case, it's at least 4. When do we use tuples? Well, we use tuples when we just want groups of values, but without the structure given by classes. As soon as we do something sophisticated with such objects, we need classes because they give us attributes, they give us routines, they give us the whole structure, invariants, and so on. But if we just want a simple sequence of values of given types without any particular mechanism to manipulate them, then a tuple can be enough. So for example, we could have a tuple of string, integer, string, the tuple type with these three components. As you can see here, we can also give names to the components. So the first one is going to be called author, the second one year, the third one title. So we could write a class, right? And that's what we've been doing so far. We could have a class book with an attribute author, an attribute year of type integer, an attribute title of type string. But a class gives us more. It gives us the ability to define not only fields but also routines. So at the level of the class declaration, not only attributes but also routines. Here, if we just want to change and access the fields, a tuple is enough. And a particular tuple, regardless of the labels here play no role, is simply going to be given as a sequence of values in brackets. And if the tuple is labeled, we can use the same notation that we use for attributes in classes, like for example t.year, where year is the tag, the label of the second component. There's a whole hierarchy between tuple types, and now you understand why we are taking this definition that, for example, tuple of AB is not necessarily made of tuples that have exactly two values of respective types A and B, but at least two values is because we want any tuple of A also to be considered a tuple. We want any tuple of AB to be considered also as a tuple of A, and so on. So that's why tuple means tuple of anything. Tuple of A means tuple of at least one element of which the first is of type A. Tuple of AB means tuple of at least two elements of which the first is of type A and the second is of type B, and so on. So this means that we can consider a tuple of AB as a tuple of A and a tuple of A as a tuple. And of course a tuple of AB as a tuple. In fact, any tuple type conforms to tuple. So this is the inheritance hierarchy. It's not really inheritance because these are not classes. These are a whole set, an infinite set of predefined types. But I'm still using the arrow of inheritance. More precisely, we talk about conformance. The features applicable to an agent A are essentially the following two. Call is applicable to any agent, and item is only applicable to an agent that represents a function. In general, an agent represents a routine. It's an encapsulation of a routine into an object, and that routine could be a procedure or a function, as usual. If it's a function, it means that the function returns a result. In both cases, you can use the feature call from the corresponding library class describing agents. And in the case of a function, you can also use item, which has the effect of calling call and then returning the result. So for example, if we have an agent representing the event left click as studied in a previous segment, then we can do a.call for that agent with the argument that is a tuple, horizontal position, vertical position. And note that I didn't say the arguments. I said the argument because formally there's a single argument which is the tuple, and that this tuple is made of two arguments. So this is how the GUI system, the graphical user interface system, can signal to the rest of the software that a certain mouse click has occurred, a certain event of type mouse click has occurred, with the two x and y values, horizontal position and vertical position, represented here as a tuple. And for a function, we would do exactly the same with item. The result would be an expression rather than an instruction, since item calls call and then returns the result computed by that call. Now it turns out that in modern IFL, there is an abbreviation for these notations. You can write things more concisely. The effect and the underlying semantics are exactly the same, but because it provides a significant notational simplification, I'm going to show it to you. You can have, instead of p.call or f.item, as we have just learned to write, the first rule is that if the last argument of a call, any call, not just for agents, the last argument of a call is a tuple, then you may omit the outermost brackets. So you may write these two examples as p.call of xyz or f.item of x. So this is kind of cheating because just a moment ago I said we have just one argument, and now it looks like we have three arguments in the first case and just one in the second case, but a value rather than a tuple of values or a tuple of one value, but still it's a notational simplification, which is okay because it doesn't cause any ambiguity. Remember that it only applies to the outermost tuple. So if we had an argument list in a somewhat devious case, which was a tuple of tuples, tuple with ABC as the first element of the tuple and D, E, F also a tuple as the second element, then you can only remove the outermost brackets. Otherwise, of course, it would become ambiguous. And then the second simplification is specific to agents. In fact, if you have an agent, the compiler knows that it's an agent, of course, it's declared that way. We're going to see in just a second how it's declared. So, in fact, the .call or a .item is not needed. It's needed perhaps for clarity, but once you get used to these mechanisms, there is no ambiguity. So you can just write P of xyz and f of x, and you can see that the simplification as compared to the first variant is significant. Now, it's really good when you start using agents to use the full-fledged notations, that is to say number 1 here, rather than number 2 or number 3, just to make sure that you understand exactly what's going on, and in particular that you remember that this call, p.call, is a feature applied to an agent which takes a tuple as an argument. But very soon you'll get used to this very powerful and elegant mechanism of agents, and you'll get fed up with having to write dot call and all these brackets all the time, so you can just get rid of the brackets and get rid of the dot call and the dot item. So we can, for example, replace the previous instruction click.publish of a tuple by just click.publish of x coordinate, y coordinate, or in our numerical example where we had this f.item of x, well, we can just write it as f of x. And so here you can see how nice it becomes, because it's really very close to the mathematical notation, which was something like sigma of f of x times step. Well, that's almost exactly what we write now, and we have the ability to have a full object-oriented mechanism, which is justified and explained in terms of object-oriented concepts, but the notation looks very much like the good old mathematical notation that everyone has been using since the 18th century, since Leibniz and Newton. A bit more about what agents are about. When you write an agent, you can have open and closed arguments. In the previous examples, all arguments were in fact open, meaning that we provide the arguments only at the time of the call to the agent. Here we need to understand the difference between the definition of an agent and a call to an agent. And the notion is very simple. When I write something like agent something, agent whatever, based on an existing routine, in all these examples it's f, well, I'm defining an agent. So that's the time of agent definition. On the other hand, when I write what we had in the previous examples, for example, in the basic notation, the unabbreviated one, p.call or f.item, then I'm calling the agent, and of course for one agent there's going to be one definition and many possible calls. And so some values are going to be defined at the time of the definition of the agent, and some values are going to be defined at the time of a particular call to the agent. So you see, for example, here that we pass all the arguments at the time of the call. But in fact, it's possible to provide some of the arguments once and for all at the time of the definition. So here, assuming that I have a routine f, which expects 3 arguments of types t1, t2, and t3. Then I could, for example, say once and for all this agent u has the arguments, the actual arguments a1, a2, a3. So when I do u.call, I don't need to provide any arguments anymore because everything has been defined. So it's going to be something like in the unabbreviated form. It's not very pretty, but it's clear. u.call with an empty tuple, because everything has been fixed. So this is exactly as if I had directly called f of a1, a2, and a3. So here you might ask, why use version 1 where we can use version 2? Well, there's a big difference, of course, is that when we use version 1, we have forgotten that u represented f. And in different executions, for example, if u is an argument of a routine to which we pass an agent, then in different executions, u could be associated with different routines, f, g, and others, as long as they have the same signatures. Whereas with form 2, we know we are calling exactly f, not a particular routine. So that's why we use agents. So coming back to open and closed arguments, we can see that in the case of u, all the arguments are closed, meaning they're defined at the time of the agent definition. In the case of z, let's look at the last one, everything's open. That is to say, it's for every call that I'm going to say z dot call of, for example, a1, a2, a3, which, as we have just seen, can also be written as just z of a1, a2, a3, with the abbreviation. But at the time of the definition of the agent, everything was open. In fact, it's possible in such cases to omit the argument list altogether because it's not very pretty or informative to put question mark, question mark, question mark. So in this case, you can just omit the argument list altogether, A0.f. And then if you look at the intermediate examples, W, X, and Y, well, X, for example, it has two closed arguments, the first and the last, and one open argument, the second one. So how do we call it? Try to guess the answer for a second. Well, we are going to call it as X of, I'm using the abbreviated notation already now, A2, that is to say, any value of type T2. Since A1 and A3, the first and the third argument had been defined, had been set at the time of definition. And for the case of Y, well, now you can fill in the details. For the case of Y, we are going to have to provide two values of types T2 and T3 respectively. So you see the flexibility of the mechanism. These are some of the calls corresponding to these examples, and you can see the details here. U.call, V.call of A3, since only one argument is open, and so on. This also is what made it possible to use the same iterator, like for all, both for a function is married, which applies directly to an object, applies directly to the target, and a function such as is positive, which applies to its argument. It's just a matter of playing with the open and closed arguments. So here we're going to use the agent is positive of question mark. And by the way, as we just saw, you can just say is positive because here all the arguments are open, but it's more clear for this discussion to show the open argument directly. And for implicit, we want to write an agent of the form agent employee is married, meaning agent applied or based on the feature is married of class employee. So this is where you find all these iterators for all there exists, dual and doeth. And I strongly urge you to look at these definitions, the routines for all there exists, dual and doeth, in class traversal. This is you'll understand everything. It's very clear and simple code, and it will be very instructive in terms of how we use agents. Agents have many different applications, and they enable us to extend the basic scheme of object-oriented programming with higher level mechanisms which are often found in what is known as functional languages. Examples of functional languages include Haskell, this is an S, include Lisp, of course, which is the most venerable of all. It goes back to, believe it or not, 1959. There's a more modern version called Scheme, but it's still basically Lisp. And a more recent one is Scala. But in fact, you don't need a special functional programming language since object-oriented languages can have, as the Eiffel case demonstrates, the full power of object-oriented programming and the full power of functional languages, that is to say, the ability to define very high-level functions that work on objects, or that work on functions that work on objects, or that work on functions. Well, you see where I'm heading. We can have an arbitrary level hierarchy of functions working on objects and functions directly or indirectly. Now, a little bit about the typing of this thing. I said this is all defined in library classes. So in Eiffel base, you'll find the classes shown here: routine, procedure, function, and predicate. Routine is deferred, and it's the class that describes all possible agents. And then if you have an agent based on a procedure, it's going to be an instance of class procedure. If it's an agent based on a function, that is to say a routine that returns a result, it's going to be an instance of class function. At the level of routine, we have call. So that's how we have the basic mechanism to call a function through the agent that encapsulates it. And on top of that, at the level of function, we have last result, which is the result of the last call, since, of course, function return result. And an item combines call and last result. It calls call and then it returns last result. What is predicate? Well, it's a particular kind of function. There are the same features, but predicate is for agents that are based on functions that return a Boolean value, true or false. These types, procedure, function, predicate, are used as illustrated here. We don't have predicates, we only have two procedures and a function. So for example, here I have a procedure P, which is declared as procedure C and tuple. So let's ignore the C for a second in all three examples. Tuple means that it expects a tuple of arguments, but because we just say tuple without any further qualification, then it means that the procedure represented by P actually takes no arguments. So we're expecting a procedure with no arguments. Q is an agent associated with procedures that take three arguments of type X, Y, and Z respectively, and F represents functions which have also three arguments and return a result of type res, or a type that conforms to res. So now, what about the generic parameter that I've omitted? Well, C is simply the name of the class to which the corresponding routine belongs, more precisely the type. That is to say, we also take into account generic parameters, and it can also be a descendant of that type. So you see why in practice it's usually enough to use any here, because if we use any, then we can represent a procedure or a function in the last case which is declared in any class, since every class inherits from any. We can apply this concept to the previous example. So remember, we had 5 example agents here with various combinations of closed and open arguments, and we're going to see what the types are. This assumes that in some class C we have this routine F which is declared, so it doesn't have results, so it's a procedure of arguments x1 of type T1, x2 of type T2, and x3 of type T3. And then in some class, it doesn't have to be in C itself. Anywhere we have a target A0 which we declare of type C, and then A1, A2, and A3 of respective types T1, T2, and T3. And so we had these 3 agents. What are their types? Well, let's start from the last one. You can see that Y has been initialized the value of agent A0.F with question mark, question mark, question mark, meaning all 3 arguments in this case are open, and as a result, Y has the type procedure of C. C is the type to which the routine F belongs, corresponding to the class where F is declared, and then the second generic parameter in this case is tuple of T1, T2, and T3. By the way, as a note of syntax, you will remember that when all arguments are open like this, we can just omit the parenthesis question mark, question mark, question mark, which is kind of heavy in notation. It doesn't hurt, but we can live without it. So just agent A0.F will work. So now try to guess what the type of X is going to be. Well, it's going to be here an agent with just 2 open arguments of respective types, T2 and T3. So we have a procedure of C and tuple T2, T3. Same thing for W. Try to guess what the type of W is going to be. Well, it's not hard. It's the same idea as before. W has 1 open argument, the second one, and it corresponds to the second formal argument of the routine F, which is of type T2. So in this case, we have a procedure with actual generic parameter C as before, and then tuple of T2 corresponding to 1 open argument. That is to say, when we call this agent W at runtime, we will have to provide 1 actual argument of type T2. For V, it's going to be the same thing, except that the open argument in this case is now of type T2. It's no longer the second one, but it's going to be the third one of type T3. And then for the final case, the case of U, we have no open arguments whatsoever because U has all its actual arguments specified at definition time, so there's nothing left to specify at call time. So in this case, we're simply going to have a procedure of C again and tuple, meaning no arguments, an empty tuple. So that's it for agents. You can see the power and the elegance of this higher level functional mechanism, and what we've seen in this lecture includes how to treat operations as objects. So this is the notion of agent. We have the ability to treat code, routines as objects, operations in general, and then to put them into data structures, for example, to pass them around as arguments to routines. We have seen a few applications of agents, there are many more, but here are some of the most important ones we have seen, and this was our starting point, that we can use agents to have a better implementation of event-driven programming or the publish-subscribe scheme, better than, for example, the observer pattern. But we have also seen applications through interactive programs in general, and we even had a short foray into numerical computing. Then we have seen that in order to talk about agents and to type agents in particular, type in the sense of giving agents types, we need the supporting concept of tuple, which is also interesting in its own right. Tuples give us a kind of lightweight version of classes. When we only need fields, we don't need routines or in particular functions or procedures. We can use just tuples as a kind of simplified version of classes. And in this last segment, we have lifted the veil on the details and seen how it works internally, in particular, how this fits in the type system of the language, thanks to library classes, routine, procedure, function, and predicate, and the type system extended to tuples and agents. So we have now extended our battery of object-oriented mechanisms with this final mechanism, tuples and agents, which provide a rich semantic extension to the framework seen before, and which makes this framework consistent and complete.